Swayam Prabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Process Technology Part 1 Module 13. We have finished the engineering materials section, and from today onwards we are going to discuss the first process, which is also one of the oldest processes in the history of manufacturing, which is called casting. And so if we look at casting, really it is one of the first steps of manufacturing that can be followed in most of the products, okay, because the reason being that, as I told you, this is one of the primary processes which will give the overall shape or size to the product, beyond which you can do a lot of suiting of the products to engineering assemblies by many secondary processes. So this is one of the primary processes of manufacturing. So in this process, the material is first liquefied, as you know, by properly heating it in a suitable furnace, and then poured into a previously prepared mold cavity where it is allowed to solidify. So therefore, the important aspect is that the liquid metal is first formulated, and there is a question of liquid metal vis-a-vis liquid alloying, which happens because of the dissolution of a second phase in that, and then it is heated in a suitable furnace, which actually takes its own or it sort of imposes its own effects by the mode of heating. So for example, if the furnace is induction based, then the heating is completely homogeneous throughout the material, but if a furnace is something where there is a wall based heating, or the heating happens through the walls, there is going to be always temperature gradients which are going to be there. So when the product is finally taken off, then you can further process it, trim it, clean to the concerned shape, something which is more suitable for engineering assemblies, etc. And so the following needs to be explored for a successful casting process. One is the preparation of molds and patterns, which are used to make the mold. Mold basically is the housing which would hold the liquid metal till solidification. So therefore, you need to be able to prepare it with a refractory material. Normally sand molds, green sand molds are very commonly available, because sand is a refractory material which can withstand high temperature and still be strong, so that is why sand is mostly used. And then also you have to melt and pour the liquid metal. So there is a lot which sort of comes into the way of this, because you are essentially passing it through a channel which is also known as the metal runner, and then there is a gate which goes or which throws off the metal into the cavity where the filling action starts taking place. And so during all this process, there is always heat transfer, because remember, the mold is always at a lower temperature than the super hot liquid metal which is flowing through it, and therefore there is always a possibility of solidification before entering. And so the processes should be defined or designed in a manner so that the liquid metal really enters before the solidification happens. And then you have to give heat to finally the solidification and further cooling to room temperature. And one of the reasons why this is important is that we assume that most of the metal goes into the mold from the gate region as liquid metal. And so once the liquid is now stationed inside the mold, and you have obtained an indication from the other side, which is also known as the riser side, that the metal has fully filled the cavity, there is going to be heat transfer of this metal to the casting walls. Pressure die casting, where a metal mold is what is basically used for filling of the metal. So there the heat transfer rates would really define how the crystal growth would take place, and in fact that also defines what is the surface hardness of the casting vis-a-vis the hardness inside, or even many other properties like strength, overall ductility, yield point, etc., related to the material casting. So therefore it is a very important aspect to be considered while dealing with casting, solidification and cooling. So and then obviously once the casting is prepared, then you have obviously it is not free of defects. So you have to have a method for defect inspection. So you first understand some of the defects, and then trying to inspect and remove most of the time non destructively, so that the casting material can be used for further processing. So, although there are several processes associated with casting, the following casting processes in context of the 4 areas just mentioned. One is the melting temperature of the job and the mold material. This is very critical, because it should not happen that the mold starts melting away and joins the liquid metal because of the superheat that the material is in. So, you have to be able to have a refractory in any event which does not have its own contribution by melting into the cast. Okay. That is how the mold would be, mold materials would be. The solubility of and the chemical reaction between the job and the mold materials also is a very critical aspect, because obviously there is going to be outgassing which happens from the mold, or even at sometimes if supposing there is some organic which cannot withstand this high temperature, this can be entrapped as a vapor pocket within the casting material. And so, in some cases these may be very harmful, because primarily it may react and make the casting very brittle. Like hydrogen solubility is a major issue in castings, because excess hydrogen may make the casting very brittle. So, these are some of the issues. There should not be a chemical reaction which formulates a hydride or a nitride or some kind of an oxide state which changes the property of the material. Obviously, the solubility of the atmosphere in the material at different temperatures to be encountered in the casting operation is also a major issue to be considered, because atmosphere itself has these gases, and if there is a possibility of solubilizing the gases within the liquid metal, then it may mean a lot of property changes because of this solubility. The thermal properties such as conductivity and coefficient of linear expansion of both the mold and the job materials, which also are very important, because you have to have an engineering dimension allocated to some material which is being cast. And so, therefore, you must consider allowances which are because of these shrinkage phenomena. Obviously, metal poured in hot state is going to cool off, which is going to make the volume smaller, and then obviously it is also going to cool down further from the solidification point to the room temperature, which is going to be linearly contracting the material further. So, therefore, you have to have sufficient allowances, so that what you are getting is the final dimension, and the final dimension to be close to what the plant dimension is or the engineering dimension is of the particular casting. So, you always need to give these allowances in the casting or in the mold design process, so that ultimately what you get is what you are looking for. Okay. So, that is how you can say that castings can be sort of defined. So, let us talk about now patterns and molds. These are most important. Pattern is something which is needed to formulate the mold. Okay. So, a pattern is a replica of the part to be cast. It is used to prepare the mold cavity. So, obviously, if we are talking about a let us say a sphere of metal that we are going to roll out of a casting process. So, the mold for that should be a spherical cavity into which the metal would go and then solidify, and so be a sphere. Okay. So, therefore, the pattern is exactly the replica of the parts, and the mold is exactly the negative of the part or the replica that we are talking about. So, patterns can either be made of wood or metal. A mold is an assembly of 2 or more metal blocks. Obviously, the mold contains the material which is used for making the mold cavity, and this material is normally a bonded refractory which consists of the primary cavity where the metal should be filled, and the mold assembly typically is made into 2 or more parts, because you want to be able to pattern the mold and extract the pattern out. So, typically the practice that is followed is that make a for a spherical pattern, for example, or for a very large casting, let us say a casting of a wheel, you should have a half and half pattern. So, therefore, there is an upper half of the mold and a lower half of the mold. Lower half is normally known as drag and the upper half is the cope, and then these two are actually having a parting line, but the pattern is kept in a manner so that you have the split pattern, particularly what we are talking about. You have half inside the lower portion and half the upper portion. So, if we have, let us say, put this material inside the refractory material, and before that you have put the mold inside, and then you have compressed the refractory material like sand, and then when you remove the upper half and the lower half, you can extract the pattern away, and once the pattern is extracted and you close the upper half back over the lower half, you have a cavity there. So, that is how you basically making the mold. So, therefore, it is an assembly of 2 or more metal blocks, as has been rightly indicated here. The mold cavity holds the liquid metal and essentially acts as a negative of the desired product, as I have already discussed. Molds also contain secondary cavities for pouring, channeling, etc., of the liquid metal into the primary cavity, and this is and also sometimes there is a cavity which acts as a reservoir for flowing the metal. So, therefore, you have the whole pouring basin, and then a runner, and then a riser on the other side, which are cavities which otherwise would not be needed if there was no requirement of pouring the metal. So, this is a sort of a metal channel, you can say, a liquid metal channel. Okay. So, this is also a secondary cavity. Obviously, this would get solidified and has to be removed once the metal piece is extracted, because the metal which is going to stay inside that cavity is also going to suffer heat loss and get solidified. So, there is a trimming action which has to be performed on the casting almost always after extraction. So, that these components or these parts, that is the riser side or the runner side, has to be totally chopped off, and that is how you recover the whole casting. So, it is obviously a wastage of material, because you want to design the riser and runner in a manner so that the wastage is very little, but still there is going to be wastage of material during this pouring process. Okay. A 4-sided frame in which sand mold is made is referred to normally as a flask. So, the mold is made of more than one part. The top portion is called the cope and the bottom one is termed as the drag, as I think I had already told you. And for production of hollow sections, the entry of the liquid metal is prevented by having a core in the corresponding portion of the mold cavity. So, supposing you wanted to make a hollow object. So, obviously, you would like that the metal does not go into that part of the mold where there needs to be a hollow. So, you have to have something called a core, and for supporting them you need some things which are like legs, where the core can be standing on, which are known as core prints, which are within the mold. So, you have a small central core and some legs to hold that core in place, so that when the metal comes around it, it basically goes around, and it is not able to go into that region which has the core. So, you can exactly make the design in a manner so that the core can be extracted later on. Okay. So, that is how you do this kind of hollow castings. Okay. So, core is very important. The projection of the pattern for locating the core in the mold are called core prints, as I have just mentioned. It is like legs which are holding the core in place. There are diverse types of patterns and molds depending on the material, the job, and number of castings which are needed. And the first important consideration which one has for designing these patterns are pattern allowances. A pattern is always made somewhat larger than the final job that is to be produced, obviously, because the excess in dimensions which are there is because of this rapid cooling and shrinking action of the material. It is not an ideal, in an ideal case, obviously, because of a thermal gradient or because of let us say a change in temperature, the metal is going to be shrinking. So, these are referred to as pattern allowances. So, such excess dimensions are always called pattern allowances. There are two categories of pattern allowances. You have a shrinkage allowance and then you have a machining allowance. So, obviously, a shrinkage allowance, as I told, is more because of thermal issues associated with the sudden sudden decrease in the temperature of the metallic system. But ultimately this casting or this primary shape has to be fitted into an engineering assembly, and it needs to be compatible with the tolerances or the overall matching with that engineering assembly. Supposing you are making a shaft, for example, and it has to fit into a certain hole. So, there has to be some tolerances, there has to be some fits of how the shaft would mate with the particular hole in question. And so, there are certain machining allowances which always need to be incorporated, where such fine machining operation on the casting would ensure that it has the exact dimensions and the tolerances that are needed for that casting to participate into a assembly, an engineering assembly. So, there is a shrinkage allowance because of the property of metals to contract when temperature goes down, and then there is a machining allowance which is useful because you want to fit these into assemblies. So, the shrinkage allowance is provided to take care of contraction of a casting. As I told you, the total contraction of a casting takes place in 3 stages. One is the contraction of the liquid from the pouring temperature to the freezing temperature. You have to understand the pouring temperature is way above the freezing temperature, and so therefore, there is going to be some kind of contraction of this liquid. There is going to be a contraction associated with the change of phase from solid from liquid to solid. So, obviously, the solid would occupy lesser volume than the liquid, because you have more intermolecular forces binding the atomic system together, and the contraction of solid casting from the freezing temperature to the room temperature is another aspect, where we are talking about the solid phase contraction. This is the phase change contraction, and this particular is the liquid contraction prior to pouring. It may be possible that you superheat the material, and the pouring temperature and freezing temperatures are way apart because of that, and because of some reasons, because you want the metal to be transported in longer runners or longer risers. You do this intentionally, that you superheat the material above the liquefaction point, or the, let us say, the freezing point. So, there is going to be a difference in temperature there, and so that when this temperature changes, obviously there is going to be a change in the overall volume of the metal which is in question. So, it must be noted, however, that it is only the last stage of contraction which is taken care by the shrinkage allowance, because these 2 stages, that is the liquid contraction and the change from liquid to solid, the contraction is very minor, and that need not be considered, and probably some of these always gets cleared off because of machining and other processes which follow the casting process. So, obviously, the amount of shrinkage allowance would depend on the linear coefficient of the thermal expansion of the solid material, that is alpha L. Once the freezing has happened, the shrinkage always, the major shrinkage always takes place after that freezing process. So, the higher the value of this coefficient, so higher is alpha, the more is the value of the shrinkage allowance, and for dimensions L of the casting, let us say, the shrinkage value is given by alpha L times of L times of theta f minus theta 0, where theta f is the freezing temperature at which the material starts to solidify. Theta 0 obviously is the temperature which is the room temperature. So, obviously, when the metal has just frozen to still hot and frozen to solid, and from there slowly there is cooling to the room temperature. So, the amount of delta L, the change in length which happens, is actually proportional to the original length, and is also proportional to the difference of these temperatures, and obviously alpha L then is the thermal coefficient, the thermal expansivity coefficient, which has to be plugged in. It is a constant for a particular material system. Okay. So, the shrinkage value normally which is given to the casting are recorded here. For example, in cast iron, shrinkage allowance is typically 1/96th, and for if you look at the machining allowance side, for dimension 0 to 30 cm, you give a machining allowance of 2.5 mm. So, these are some thumb rules which people have generated who have been running these casting industries. If you have machining allowance 30 to 60 centimeters, the for a dimension 30 to 60 centimeters, the machining allowance would be about 4 mm, so on and so forth. So, similarly, you have cast steel low carbon, which has a shrinkage allowance 1/48th of the actual dimension which is in question, aluminum which is 3/192, bronze 3/192 again, and brass 1/48 again, and then the machining allowance for the dimensions are given here as 3 mm, 1.5 mm. Similarly, for 30 to 60 cm dimensions, the machining allowance is 4.5 mm or 3 mm for cast iron, cast steel, and aluminum, and so on and so forth. So, that is how some of the thumb rules are defined in terms of what shrinkage allowance or machining allowance will take for various material systems in question. Usually, a cast surface is too rough to be used in the same way as the surface of the final product. So, as a result, machining operations and surface finishing operations are needed. I think I have just mentioned about it here, and the other more important aspect which I would like to consider is that apart from these 2 allowances, there is also something which needs to be provided to facilitate the easy withdrawal of the pattern. So, it refers to some kind of a taper, because obviously, if the pattern is straight, and it has to be removed from a refractory wall, as vis-a-vis if the pattern is tapered, the taper always gets removed quite easily. So, you have to have some taper allowance, and normally it is half degree to 2 degrees which is given. So, for example, for casting a cylinder, you need to not have the pattern exactly straight, but maybe a little bit of 2 degrees or so taper. So, that it is easy to remove this pattern out while you are making the mold. Okay. So, so these are normally some of the thumb rules that are used for doing pattern designing. So, we will talk about more in the next module about how further we design the mold, or how further we design the runner and the riser, which are two most important things to ensure that the metal flows well and flows into the cavity before it freezes, and also rises on the other side to indicate that the cavity is full. So, thank you as of now. Thanks.